Okay, last but not least, for our ANOVA series in R, we're going to cover how to do a mixed factorial. So this is a two-way ANOVA with one repeated measures and one between subjects. So with a mixed design, you're going to look at both Levine's and Mauchly's to assess homogeneity and sporicity, if you have more than two levels for sporicity, because you have both in your analysis. You have a repeated for sporicity and between subjects for homogeneity. I'm kind of assuming you've watched some of my other videos, but if you haven't, remember you will get main effects because you'll have more than one variable, and so you'll have just that IV all by itself, and interaction effects where you're looking at the variables, the differences in means by condition. So I kind of made a little chart in each of my ANOVA analyses documents. And so if the main effect is between subjects and there are only two levels, you just interpret the means. And that's true for both. Because remember, ANOVA and T are the same thing when you only have two levels, so don't run the test twice. If you have more than two levels and you're interpreting a significant main effect between, you should follow that up with likely an independent t-test. And we're going to talk about Bonferroni as a good correction. If you're doing the main effect for repeated measures, make sure you do dependent T. So it's very easy in R because everything is in log format, to confuse the two. So make sure you run the right type of t-test follow-up for your post hoc. And that'll also be true for the interaction, especially important depending on which way you decide to split the variables. So, make sure the sound's off here. What we're going to do is walk through a mixed design and follow up with the interaction. And if our interaction is significant, often people ignore the main effects because why interpret the main effects? If the interaction is significant, it saves you type 1 error. And so this particular design, we're looking at high backward strength. This is very similar to my double repeated measures example. And so we know higher backward strength is a problem when people are rating word pairs. If I give you cheese to cheddar, the fact that cheddar to cheese is very related really messes up your ability to interpret the forward relationship. And so we told people to ignore this as part of some instructions we gave them. And it's kind of tied to judgments of learning. You get the same effects. So we're trying to apply that to these judgments from memory and see what happens. So we're going to load some data, and we're going to test our between subjects IV is group. So they were either in a regular judgment task or a debiasing instructions task. And they only got one set of instructions. And then we looked at words that were high and low in BSG strength and just looked at a range of forward strengths. So seeing really if that backward strength affects it. Now in reality we did this as a 2x2x2, but just to make this easy, we're going to do this as a 2x2. The dependent variable is our rating of those word pairs. So to do power for mixed design, what we're going to do is pick Ttest, and then come down here and pick ANOVA repeated measures within between interaction, because that's what we're interested in. I'm going to hit determine, since we don't tend to use F very often. I'm going to pick direct to estimate from eta squared. Let's see what I did in this example. I did a large effect size of 0.25. Calculate and transfer to main. Alpha is 0.05. Power is 0.8 because beta is 0.2. Now the number of groups here is based on the number of levels for between subjects, so literally the number of groups. The number of measurements is the number of levels for repeated measures. So it is a 2 by 2. Correlation among repeated measures. So 0.5 is a good estimate. I wouldn't go too much higher if you didn't know better, because then you'll be underestimating the number of subjects you need. But if you're really wanting to be very conservative, you can lower that number. So the higher the correlation for repeated measures, the stronger the power. And then the non-sporicity correction would be assuming you don't have sporicity. In this particular example, we only have 2 levels, so we don't have to worry about sporicity. So I'm going to leave that alone as well. It says I need 10 folks to get at least 80% power, which is the beauty of repeated measures designs. I have way more than 10, so we'll be good. So that's how you run power for a mixed design. Okay, so let's walk through this. So the first thing you want to do, I set my working directory. Now I'm going to import the data. So I'm going to call this master data set. And then it's rm2anova.csv. Let's look at what's in this data set. So I actually have a bunch of variables of subject number already, which is good. I need it. Grouping variable, and then I have some forward string stuff. This is the one I use for my double repeated measures example. And then the two backward string variables I'm interested in where I averaged those columns. So first thing I want to do is just drop all the columns I don't need. So we're going to make our master data set just to be square brackets. I want columns 1 and 2, keep my subject number because I already have it, and then 1, 2, 3, 4, 5, 6, 7, and 8. Right? But if you aren't sure, you can do names, the master, and it'll give you some numbers out here, and that'll help you figure out what numbers you need, 7 and 8. So I gotta concatenate those together, 7, 8. And close parentheses, go. So that dropped all the columns I didn't need. That's much easier to deal with. So we're going to check the accuracy of the data. It should be factored, this my group variable, and it should not go below 0 or above 100. Subject number can, but not the BSG variables. So let's run a summary for that. Okay. So my grouping variable is fine, it's just the labels are ugly. My subject variable I just can ignore. My BSG is pretty good. It doesn't go below 0 or over 100. If I wanted to fix the labels for my variables, what I could do is use the factor function. So factor, then the name of the variable you want to pick. Levels, so I have to type in currently what are they. So it's dbias lowercase and jam lowercase. And then labels, now in the same order. Now I can make them pretty. So before we get started, let's try a table of what that variable looks like. Now I can see my summary right here, but this is what it looks like now. Let me run my factoring code. I'll run that table again just to make sure that it didn't do anything wacky and it didn't wipe out my levels. So first couple times you use factor, it can be very easy to erase your data. So be sure you run a table or a summary to make sure you didn't do that. The other thing to do is if you did do that, you could go back up here where you imported the data. So if you use the import dataset option from text file, be sure that you're copying the code where it's actually importing the data and sticking it in your script so that when you screw up, you can just back up a couple lines. All right, so with that summary function, I can see I don't have any missing data. Even if I did have missing data, it would be more than 5%, so I wouldn't want to estimate that much data. I do want to screen this in wide format that incorporates the fact that each person is their own unique snowflake, and so therefore they have their own row, and it accounts for the correlation between total brain fart because of that one pop up there. Accounts for the correlation between measures as well. Okay, so it helps make sure that if a person is an outlier, then outlier because the entire row is a little nuts and not just one particular data point. Okay. But because they're in that format, we can use Mahalanobis because we have more than one column for each person. So we don't want to ignore the fact that person 1 is person 1 the entire time for all 2 levels. Typo there. Okay. So I'm going to use Mahalanobis to check for outliers, which is different than between subjects. For all between subjects, I have to use z-scores because I only have one column of data. So we're going to create those Mahalanobis scores. by looking at the master data set, but we only want to screen the between subjects pieces, or the contiguous part, so don't screen the subject number. So I want to screen 3 and 4. For centering, I'm going to use column means. And then covariance. So it's the same data set name each time. Oops, if I can type. So we want to use this a couple times. So let's create those Mahalanobis scores. But I have to have something to compare to, so I'm going to create a cutoff score. And that's going to be Q chi-square, because we want a cutoff or a quantile. So 1 minus alpha, which we're using 0.001, so you can put 0.99 here. But 0.001 is our big important rule. It has to be at least 0.001 outside the range of the data, not 5%, or we'd be eliminating a lot of people. So that's 1 minus alpha. My degrees of freedom is the number of columns that I used above. And then the rest of it we can leave alone. So that gives me a cutoff score of 13.82. But if you aren't sure what your cutoff score should be, you can just type cutoff again. This gives you the actual cutoff criteria. And then you can also ask for in-call for number of columns of our data set. And that will give you your degrees of freedom, just in case you aren't sure. So with 2 degrees of freedom, our cutoff score is 1382. I'm going to take a summary of how many people are less than my cutoff score. Hopefully everyone, and no one's an outlier. But unfortunately, that's not the case. So true here is good scores, because we're seeing how many people are less than the cutoff, which is what we want. False is an outlier. So we're going to exclude that outlier, create a no out data set by using the subset function, where the master data set, it's Mahal less than cutoff. So that's why I did this in this order, where you're looking for falses, because it matches how you would subset the data. So we lost 1 participant. I've looked at this data before, and that participant actually did the experiment correctly, so it's kind of funny they're an outlier because they did what we wanted them to do, but that's not what people normally do. So in this tiny example of an experiment that I've run before, our outlier is because they did the data correctly. So normally you would want to probably exclude those people. Okay. Now additivity we have to look at a little bit for repeated measures designs, but only in the sense that we don't want columns to be perfectly correlated or it won't run. So what we're going to do is use the correlation function. So we're going to create our correlations by inputting that data set. And I don't have any missing data, but in case you did, it's pairwise complete obs. And I could look at the correlations, especially for power estimations. So I could up that correlation between repeated measures to 0.6. But if you have a huge data set, the symbol for number function is really great at showing you what, like a big chart in a simple way. And you basically don't want any ones that aren't on the diagonal. So these are them correlated with themselves. You want that. You can't have ones anywhere else. Otherwise, repeated measures won't run. So we do expect correlations to be fairly high. So 0.9 is a little, can happen. Like with factor analysis, we often want them to be that high. So generally, we're just looking for stuff that isn't 1. All right. So we're going to test the rest of our assumptions here. So I'm going to do my assumption setup. And this is the same as my many other videos. So I'm going to create a random variable using chi-square. And I tell you to watch the data screening video to really get a good feel for why I'm doing this. But so I'm creating a random variable that's chi-square distributed because our data should be randomly chi-square distributed when we look at residuals based on the number of rows. So I need as many random numbers as I have people, and 7 because it's a magic number and it works well for me. So you can pick a number over, as long as it's over 2. I'm going to run a fake regression predicting that random variable with my data. So I'm going to use the dot function here. And then data equals no out. Now, one problem I have is I do have a subject number already. So I really should drop that subject number while I test my data. But what I found when I ran it with and without the subject number is that actually does not matter. But you, in general, don't want to include, like, it should still be randomly distributed, and it shouldn't matter. And it didn't, but in theory, we should be screening with only the variables that are really part of the analysis. So I might kind of drop that subject number temporarily. And I notice it didn't go away, it just isn't included in my fake analysis here. So because we have this, our data predicting a random set of data, we should get a random distribution, but we're going to scale that distribution and standardize it to make it easier to interpret. So I'm going to get the standardized residuals by using our student function. It's the studentized residuals. And I'm going to get my fitted values by scaling or z-scoring my predictive y-hat scores. Now, because these are predicting a random variable, they should be random, but since we standardize them, they should be randomly distributed around 0, because some people will be good, some people will be bad, but it should still be all kind of nicely falling around 0. So speaking of that, let's look at normality. That's a histogram of the standardized residuals. It's pretty good. It's mostly between 2 and 2, and it's mostly centered over 0. Let's get a little bit of a skew out here, but it's okay. We do have more than 30 people, so we don't have to worry too much, but I could rerun my randomness. Look at it again, just to make sure. This time it's a little more skewed, but again, I have 30 people, and ANOVA is fairly robust to normality violations, but that's not super abnormal. Let's look at linearity. It's QQ norm of our standardized residuals. And if you have this code, you can copy this and paste this. This part really doesn't change. So AB line to make it more interpretable. This is probably one of the prettiest ones you'll see all year. That's pretty close to the line. So this is a fairly pretty graph. So it is linear. Let's look at homogeneity. So I'm going to make a plot of my fitted values versus my standardized values. I'm going to add a 0, 0 line and a vertical 0 line just to aid in interpretation. And this graph is like sort of iffy. It's 2 to 2 on the horizontal axis here, but on the vertical axis, not so much. So we really should be centered evenly around 0. And it's not just like one dot driving this up here. So let's try running it one more time. See if it's consistently bad. Yes. So we really need to make sure homogeneity is okay with our data. And we'll do that by looking at Levene's test. All right. So what we want to do is look at Levene's. But to get Levene's, we have to run the ANOVA. We already have a subject number, so I don't have to do anything. But if you did need a subject number, here's an example of how you do it. The other thing we need to do is make sure everything is in long format. So currently this is in wide format where each repeated measure has its own column, and I need to melt that data down to long format. So I'm going to use the reshape library. And I'm going to melt my data. So I'm just going to call it long data because that makes sense to me. The function is melt. What you do is put in the dataset name. ID equals any variable you don't want to change. So I'm going to have to say I don't want group or subject to change. Measured are the ones we want to melt. So we got BSG low, BSG high. Let's make sure that ran correctly. So we've got our group variable, our subject variable, that stayed. BSG low and high, and then their value. So I could sort by subject. Each person now has 2 lines. Now, One thing I don't like about reshape is that it renames these columns variable and value, which is like, I mean, I get it, but bleh, right? So let's rename this. So call names of the long data equal, I want to leave group alone, I don't want to leave subject alone, those are fine. It's these next two that are bad. So this next column is our BSG condition, and the last column is their rating. And all that did was change the names of them. When you're changing the names of data set columns, don't use spaces. For the love of bananas, do not use spaces. It will cause you a lot of problems. You can use very descriptive names, like really long things with underscores or dots or something, but no spaces. It will let you do it, which is unfortunate because you shouldn't. Okay, now that the data is in long format, we're going to run this ANOVA. So it's the EZ library. So we got EZ ANOVA. And we're going to do data equals long data. DV equals rating. Within, is BSG. Between is group. Within subject's ID or participant number is subject in this one. Type equals 3, so you get type 3 sum of squares. So all of that is here. So this probably is one of the longest ones you'll write unless you're trying to do ANOVA, which I would warn you it does not do correctly. Let's run it and look at our data. Okay. Now I didn't get Levine's. So I don't know what happens, but sometimes when you run this as a mixed ANOVA, you don't get Levine's. And you kind of want it, and I kind of need to look at it. So to get Levine's, I could run Levine test, which is in the car library. I'll talk about that in my ANOVA video. Or I could just copy this whole thing, take out the within part, run it again, and then there's Levine's right there. Okay. So Levine's test is not significant. We're looking for less than 0.001. And it is not significant based on that criteria. And so I think we're okay for our homogeneity problems that you see over here. So going back up here, what I've got, and here I can pull it up a little bigger here, are my effects for the ANOVA. Now we didn't get Mauchly's because we only have 2 repeated measurement levels, and you won't get it then. So I'm going to want to interpret here. So my grouping function is, or my grouping variable is significant. My backward strength variable is significant, but the interaction is not, which is unfortunate and is sad. If you are terrible at understanding scientific notation, you can turn that off. It's options, SciPen equals 999. Without scientific notation. So there's your giant p-values. So first 2 are significant, the last one is not. Our effect size out here indicates that they are between large and medium effects, and that the interaction is very small. Okay, so a bunch of examples here in case you had some repeated measures you needed to correct with Mauchly's. But this is how we write it, at least in APA style. And so the first 2 are significant and the second one is not. Since they're both 2 levels, all I would do is interpret those. So I'm going to use tapply. Let me show you the with function. Haven't done this, I don't think, in my videos very often. So with, and we'll do long data. We can do tapply, and that just keeps me from having to write long data 4 or 5 times. So it's DV first, rating, and then let's go backward strength. Yeah, and then go away. Mean. So that gives me the means for low and high. And so what happened? Well, people rated the high ones higher. They're not really supposed to, so in a theory, we would want this to not be significant, but we know it is. So we're really pushing for that interaction, but it didn't happen. I could do this whole thing again, but instead of backward strength, look at group. And what happens is, with the instructions, everyone lowers their overall ratings, which is good because people overestimate, but we really wanted an interactive effect where they also, they lower their ratings and they change their slopes. I could also get my condition means to analyze those if I needed to. So I can use tapply and the with function to get my means. Could change this and get standard deviations at n. So standard deviation here for each group. And that's where probably a little bit of the homogeneity problems are coming from, is the difference that one group is much lower. And I can use the length function to get the number of people in each group. Okay. Now these are the same for BSG low and high because that is the same people. Right? So there aren't 73 plus 73, it's 73 people in each half. Okay, well, normally what I do now is sort of stop and be at a bust because my experiment sort of half worked. But because this is an example, I'm going to show you how to analyze the interaction. So I have a 2x2, which makes things a little simpler because no matter which way I analyze it, it's only 2 tests. So I could split going across or down. And let's see what I did here. You pick based on a hypothesis, or you'd pick based on the lesser number of tests. And either way, we're going to have to split the data set into chunks. So let's see here. I made myself a little table. So I'm going to compare within each instruction group BSG low and BSG high to see what the difference is between the two, in the hopes that one of the instruction groups has a smaller difference than the other group. Because the instructions are supposed to help eliminate those differences between high and low. So that means I need a jam data set and a debias data set. So I'm going to use subset here on my long data. And I'm going to split jam into, it's group equal. Now, I call these descriptive names, so I probably need to look at what they're called again. So let's look at that. Alright, so here are my jam instructions. I'll copy this. Be sure you do double equals here, or nothing will happen. Okay, so my jam data set should be smaller than that data set, so it's about half. Then I'm going to do the exact same thing. Create the other half of the data, my debias data set. So that's the only bad thing about using really awesomely descriptive labels, is if you're subsetting, you do have to copy them precisely. And that split it into the other half. So the total here should be the total number of lines in long data, and it is. Now that I have it split up, what I can do is run a pairwise t-test with the Bonferroni correction. And here, where I got these from was from using tapply to get the means of standard deviations. This sort of little chart really helps me run effect size codes. It also helps me make sure that it's clear that we're running this pairwise, so 2x2, and what exactly I'm comparing. So I'm comparing jam on both of these, and I'm comparing low versus high, debias, low versus high. So this is a whole lot of stuff written here about making sure that you run the right type of t-test with your post-hoc here, and making sure you use the right data sets. So let me think about this. I'm running low versus high. And ask yourself, are people in both of those groups? Yes. Or both those levels? Yes, they are. So this needs to be a dependent t-test. If I had split it the other way, it would have been an independent t-test. So we're going to use pairwise t.test. Okay. And this is another good place for the with function. So I'm going to say with the jam data set, what we're going to do is the DV is rating, the IV is BSG, because I can't use group because that's what I split on. Paired equals true. Make sure that's in there so I get a dependent t. And p dot adjust method is Bonferroni. If I can spell. Make sure to close my with function here. That tells me that they are significantly different. Now what I can do, the cool thing about with here, is do that whole thing again and just change the name of the data set here, instead of having to do the $sign stuff here and here. Both are significant. Okay, so I filled that in. High ratings are higher than low. High ratings are higher than low. Okay. That does not indicate an interaction right now. So what I'd want to do, if this were significant, is look at the effect size and see if the effect sizes are different. So sometimes with an interaction, the directionality of the effect is the same, but the effect sizes are different. And so what you can do is you can use Moat, or you can load my effect size script that I wrote. So I'm going to run that whole thing so I can get all of the functions I need for that. So after you run that, you should have a whole bunch of functions out here. And to make a long story very short, what we're going to do is do D depend to T, because that's what we have, but averages. So I'll need to enter each mean and standard deviation, and then overall N. And that's what this table's for. So it allows me to know exactly what I'm comparing, and this part makes it a little easier. So the mean for time 1, it's not really time 1, but you get the idea, is 68. Standard deviation 1 is 10.84. Time 2, or measurement 2, is 82.72. And SD2, is 8.29. N is 84. There's only one N because it's dependent T. We're going to set alpha at 0.05 and the number of decimals at 2. That gives me my mean and confidence interval for each of the independent levels, and then, or dependent levels, sorry. Gives me my D of 1.51, so it's a pretty big effect between the two, and actually my confidence interval for D as well. Now just to cheat, I've actually already done the second one as well. And so we get, oh, that looks like maybe, so there's the second one. I got 103. So the effect sizes are both large. So there's no interaction because the direction is the same and the effect sizes are roughly the same. All right, excuse me. What you'd want to do next is create a graph. Now I have several videos on ggplot, and you should watch those if you want to really get more into graphs. But what I'm going to do is load my theme coding here. So I have this big block of code to make my graph not hideous. And then I've created my blank plot here. So I'm going to use long data. I'm going to fill it with group, or that X is going to be group. So whichever variable you split on should go on X so that the bars line up next to each other for what you're comparing. The next thing over is Y, or the DV. And then fill here is what the bars are going to be, so the legend is going to be BSG, which in my example today I did as caps. So if I just look at the bar graph that I ran, now I have this blank but fairly hideous graph. This first stat summary calculates the mean and creates the bars. This second stat summary creates the error bars as a confidence limit with alpha's 0.05 is the default. My theme coding here cleans that whole thing up so it's not so hideous. XLab changes the X-axis label. YLab changes the Y-axis label. And then let me show you what that looks like. So now one thing I want to do is change this BSG, this stuff out here. I called it fill here. So I need to do a scale fill here. Name is for the name label here. Labels are the labels here and here. And then values are the colors. And then when I added one more thing, chord Cartesian, that changes what the y-axis limits are. So I'm going to go from 0 to 100 because these values go up to 100. So don't stretch the graph in an inappropriate way. So now my graph goes up to the correct y limit. It has the very pretty labels for everything so you can know what it is, and error bars. And so that would be an important piece to include for your write-up. The last thing that I have in my example document, which you can download from our website, stattools.com, or stats tools with the S. It looks like stat stools sometimes, is an example of what this write-up looks like and what you should include in write-ups. And so all of that taken together is a mixed factorial ANOVA in R.